So I always find it helpful, I hope my voice is loud enough. I'm too tall for the microphones, and is this better? Can everyone hear me now? Okay. I always find it helpful to show a physical description of what it is Integran brings to the table. This is a ping pong ball that has been electroplated with Integran's nanotechnology. The nanotechnology is really the coating that we make, and these coatings can be exceedingly thin. The coating in this case is about 4/1000 of an inch thick, or 100 microns. And the end result is a ping pong ball which I can stand on and not have any problem breaking. I'm about 250 pounds. So we can generate an electroplated coating. The nanotechnology is in the coating, and I'll go into more detail there. But what makes this useful is when you start combining the coating with other substrates. And some of you in the back won't be able to see this, so I'm happy to meet you afterwards and talk a little bit more about it. We generate a lot of parts that make use of this coating. And here's an example of a fishing reel stem. It's made out of plastic. We then add our Nanobate metal coating to the outside of it. And the end result is something that's much stiffer, much stronger, and in effect replaces a machined aluminum part. Now the benefits really come out when we're talking about things like cost and weight and amounts of parts that you can process at a given time, because machining a complex part like this can take quite a bit of effort and can take quite a bit of cost. And you have to have a capital of machines ready to do that machining for you. Injection molding, on the other hand, is something that can be done very quickly, and that's where we're focusing our technology. So this injection molded part doesn't really have much structure to it until you add the electroplating nanostructured metal on the outside of it, and now you have a part that is equal to a machined aluminum. That's just one example of the kind of technology that the Nanobate coating can bring. I'll give a number of different examples, but the basic technology is sort of rooted in this Hall-Petch relationship. As you take a metal and you shrink the grain size of the metal down, you get drastic increases in the yield strength of the material. This is so as you take a conventional polycrystalline material and you decrease its grain size, you get big increases in the yield strength, and also you get very high increases in the hardness of the material. Now this does come at some consequence. You do lose a little bit of that ductility of the material, but the way that we process it, we're able to retain enough such that it still has a good degree of engineering ductility to it. It can absorb energy before failure, unlike a ceramic. Just a little bit more detail, and this is a very old image, so I'm sure some of the people here would be able to process a much more pretty picture of what a nanostructured metal looks like. You know, essentially you have a polycrystalline type of material. These are more powdered. You shrink the grain size down, and you get the increases, as I mentioned, in yield strength, ultimate tensile strength, hardness, and as I'll go into a little bit more detail later, we don't have that consequence in ductility. So the way that we get this, electrodeposition, conventionally speaking, you use direct current plating, and you put it onto a substrate. The substrate, hopefully some of you can see this image, the substrate's represented on this side here, and the electrodeposited coating in a conventional sense is represented on this side. The very first few layers end up being very fine-grained, but as you continue with the electroplating process, you quickly end up developing more polycrystalline structure, nothing that's really all that structural in nature. But what we're able to do is, so like the base patents around the technology were that you use a pulse plating approach, and that way you're always introducing the nucleation phase as opposed to the grain growth phase. And if you maintain that, as well as through our proprietary bath chemistries, you're able to keep the grain size of the material very, very small, down to the 20 nanometer range. You're able to do that for very essentially infinite thickness and keep the properties uniform. The grain size is consistent through the thickness, and what we're dealing with here is a fully dense material. We're not looking at consolidation of powders where you might have some degree of porosity. And it's that layer of full density that allows you to have the engineering ductility. So this brings kind of a quick summary. Very strong and hard material. Has good toughness. The elongation to failure is typically between about 6 to 8%. And it makes excellent structural claddings to add to different substrates. Most of you know much about the conventional metals, but what we find is that it's a good mix, and if you add it as a structural cladding to select substrates, you end up with hybrids that have a very unique set of properties. The core businesses that Integran has, we generally do nickel, cobalt, copper, and iron, and based alloys of those. And we can generate parts that have the Nanovate structural cladding on them. But actually, a little bit more recently, we've also started going into pure Nanovate metal parts. So this is, in some case, we'll build up, say, 4/1000ths of an inch and just provide it as a structural foil, or a shim, or in some cases, we actually build up enough material such that we build up a bushing out of this material. Very useful for cases where the conventional approach would be to have a large metal rod or such and have to machine away all of what you don't want. A little bit more background on Integran. So actually this number is a little bit outdated, but we've been around as a standalone company for about 15 years. We do a lot of research and development for both US DoD and other academic agencies, and we do a lot of work for customers as well. We have a lot of intellectual property covering our technology, both in a process-related sense as well as in a product-related sense. The company, the technology is based in electrodeposition, so in a lot of ways we can be very competitive with the kinds of costs that you would expect to see out of conventional electroplating processes. And we're headquartered in Toronto. We have a 52,000 square foot facility. A lot of that is our plant, which is where all of our parts go through. And just recently we've got our quality certification for AS9100, and this is to work better with our aerospace partners. And we do a little bit of defense work as well, so we are compliant with the ITAR program. The technology is something that has been adopted around the world. We're looking at nuclear reactors. That's actually where some of the first technology adoption was. We have a number of people who are licensing our technology, such as Enduro Industries in the US. We have Pratt & Whitney in Quebec. We have a US DoD depot in the States. And we very recently have helped one of our electronics customers get a facility in China so that they can integrate that with their manufacturing lines. So you may start seeing some parts with our stuff on it soon. To give you a little bit of a different flavor of how this really works, so we've got the Nanovate, that's the trade name, Nanovate structural cladding. It's got a select set of properties that are beneficial. High strength, toughness, stiffness, etc. But what we can also do is add that to the substrate, and by designing the coating and the substrate together, you get a hybrid that has a unique set of properties that can, in a lot of ways, outperform a conventional, say, fully metal, fully plastic, etc. part. This is an example here of a polymer core and a Nanovate EM, which is our low-frequency electromagnetic shielding coating. And if you think about a cantilever beam, the location of the Nanovate metal is placed where it provides the most benefit, because that's where the largest bending stresses are. Going back to what it is that Integran can offer, so we have a number of different alloys that we focus on. We have our N1000 series, which is primarily a nickel alloy, and that's very good for the addition to composite substrates, to polymer substrates. We have our N2000 series, which is nickel alloyed with iron, and in that combination we have largely two different families. One of them is for low-frequency electromagnetic shielding, kind of like a permalloy composition, and the other one is a higher iron content, about the composition of an invar. So what we have there is a nanocrystalline version of invar, a low coefficient of thermal expansion material that can be added to, say, carbon fiber composites, providing a much better CTE match as well as surface hardness, etc. for composite tooling. Our R3000 series is a cobalt, and that's very good for sliding wear. Our hard chrome replacement, galling resistant materials for, say, titanium to titanium matching or aluminum to aluminum matching. And finally, our copper 4000 series, which is an example of an electroformed copper shape charge liner. But this is a material that's picked up a lot of interest for high corrosion resistance, good ductility, as well as good electrical conductivity. So I'll go through a little bit more in detail a couple different ways in which we use our nano-bait metal, one of which is structural plating, so that'll be on plastics, composites, and aluminum, all in different respects to provide some sort of value for our customers. The second family is in that corrosion and wear protection. This will focus mostly on that cobalt family that we have. And then I thought I'd throw this in there as well, just because it shows a little bit of the flexibility of the process, the ability to produce fully nanobate metal bushings, and that is what helps sort of differentiate ourselves from a conventional plating. As I mentioned with this fishing reel stem example, the nanobate addition to the plastic is a very good, offers a number of different advantages over something like machined aluminum. This is a very quick summary. This is sort of like the one-pager that we'll provide to people. But what you do is you combine the very strong, durable surface hardness with the nanobate metal, and you add that to the very lightweight polymer core. The combination ends up giving you something that's about 30 to 40% lighter than a machined aluminum counterpart, and that's matching about the say peak loads or so. But you have added benefit because you have a surface hardness close to tool steel. We're talking about material that has hardness between about 50 to, in some cases, 65 Rockwell C hardness. So it's a very durable material, scratch-proof, dent-proof, impact resistant. So when you compare this value here to something like an anodized aluminum is good, but that hard anodized layer, it can break down, and when it does, you're exposing the aluminum underneath, whereas our material, it's got hardness, but it's also got toughness, so it stays around and it can absorb a lot of energy before breaking away. This is an interesting point here, the leading edge retention versus aluminum. And it'll make more sense if we talk afterwards, but we produced parts for aero engine manufacturers, and what we found is that the ability for that, say, tapered section to maintain that edge is important for the aerodynamic properties to be maintained, whereas if you take an aluminum part and it gets a dent on that leading edge, you suffer quite a bit, not only in structural performance, but in aerodynamic properties. And then in a lot of cases, what we're doing is we're adding that look and the feel to metal. Some people just kind of come to us with polymer parts and say, you know, our customers don't really like polymers. They don't like the look of them. They think of them as something that might be able to break, despite the fact that some of the peaks out there are very good. Some of the PIs out there are also very good. But it's just it's an aesthetic thing, a human factors thing. Yeah, so as I mentioned, Nanobate NP is currently displacing machined aluminum aero engine components. This is because we can bring a reduced weight, a reduced cost, and we can manufacture something in some ways quite a bit faster. Just a couple of commercial examples here. I don't know how many of you are sports fans out there, but if you are, I can talk to you afterwards as well.
I've kind of gone over this quickly, but this is it in pictorial form. We're combining with the nanobate metal the properties of the metal over top of a polymeric substrate, and because of the location of where the nanobate metal is, you really get the biggest bang for your buck. So, as I mentioned, the nanobate added to different substrates provides different value. In the case of carbon fiber composites, what we found talking to a lot of customers is the carbon fiber composites, they're very good at being lightweight, they're very good at being strong, very good at being stiff. Really, you don't need to do much to them unless you end up taking this carbon fiber part and you expose it to some sort of impact or some sort of damage or subcritical event, and then you expose it to some kind of fatigue, for example. And you find that, though you take that composite part and look at it, you can't find the defect so easily. Over time, you will find that the composite part can break. This is one example here. The folks at Cervellia here came to us because they had a composite steer tube on their very lightweight, very high performance composite bike, something that'll sell for like 10 grand. And you take that steer tube and you hit something while you're riding it, and there's a subcritical impact introduced right into this area here. You then undergo some sort of fatigue test, and one, you don't know when it's going to fail, but you know it's going to be less than its unimpacted version. So they were finding that this part would fail after like 2,000 cycles or so, on average, after an impact. Well, what we were able to do is add a strong, tough structural cladding to that composite part, and now when you undergo the impact event, the metal takes the brunt of that, and you're able to retain the properties of the composite so that it still has its performance. Afterwards, they were able to run that same test. It ran for 200,000 cycles, then they just shut off the test because, all right, that's good. I don't know if, how many of you might know of Integran in terms of hockey sticks, but this is something else that we've been going at a lot recently. So we've launched this other brand, it's called the Colt hockey stick, and carbon fiber composite sticks. Maybe you've seen it on TV. It's a pretty rough environment. A lot of hacks kind of introduced into this zone near the blade. Then a player takes a shot and finds that the blade just disappears underneath and cracks in half. Well, what our metal was able to do is reinforce that area to take the brunt of all those hacks and then retain the performance afterwards. This has been a really interesting one because we're actually just selling it ourselves instead of going through some other manufacturer. I was trying to upload the video into this presentation, but it was a pretty big video. The overall story is... Did you try it? What's that? No, it's this player here, he took a composite hockey stick, hit it over the goal net, okay, it broke. Didn't really know what to expect from the nanobate material, just kind of hacking. I'd recommend taking a look on our website if you want to see more of it. It's kind of a fun little project. Golf shafts, baseball bats, we've done a lot of other sporting goods as well. And then here, this plane here is showing the rain erosion performance that you get with the addition of the nanobate metal. Composites, on the other hand, don't have a great degree of that. So this more or less goes over what I was talking about here, but to give you a specific example, the composite bike fork added with 50 microns of nanobate gave you a 20 times increase in the fatigue life. That's fairly important. But what made this special is something else that Integran has designed and invented essentially, is this Integran material, which enables a good level of adhesion between the composite and the nanobate metal. And that's also something very important with all of our product lines, families, is that you need a very high degree of adhesion between the nanobate metal and the substrate in order to effectively couple the loading and transfer the load between the substrate and the coating. So in all cases, this is something we looked at a lot. This is more or less pictorial example of what kind of tests we do to show the adhesions. This is a pull-off test, but more or less nowadays we use the heel strength strength. So this is an example of a small coupon that's been treated with our in-bond material and then metallized, and we peel the level, we peel the top level away from the composite substrate, showing that you get a good degree of adhesion. I've got one example in my bag here, which I can show you afterwards. Let's see. So yeah, we can generate coatings on materials. We can generate also self-standing nanobate materials. In this case, we generated seamless liners that we then used as ID layers for composite tooling, composite like actuators, tubes and such. The composite's good at providing a high strength and stiffness and low weight, but it's not very good at resisting chemical attack. And so a very thin liner of our material inserted in the ID, or you wrap your composite around the OD of it, and you've got a material that can be a lightweight actuator with a very high level of vacuum integrity. We also have a little bit of flexibility with our program. This here is an example of kind of like a 40mm grenade launch tube that could be generated with the nanobate metal liner shape to give you some rifling, and then composite added around the outside, and that would replace something that's a fully machined aluminum launch tube. The nanobate on aluminum is an interesting combination. We've got a lot of people who've come to us for titanium. We've got this titanium part, and you plate it to improve its surface durability or something along those lines. But what we actually suggest in that case is, let's move to nanobate on aluminum. Aluminum's a little bit difficult to get that level of adhesion to, but we've worked out the process to do so. Aluminum offers you, compared to titanium, a lower cost, an ease of machining, and you when it comes to the surface hardness, we find that the nanobate really takes care of most of it. But nonetheless, here's an example of, this is a golf club product. They were using aluminum, actually they were using steel even before that. But when they put the steel in their golf club bags, and they have a number of other clubs kind of rattling around and hitting the faces, they find that the faces dent. And that's not something they want to look at or even use for accuracy or for aesthetic purposes. So they tried to move to a titanium, still didn't really have the surface hardness. They tried moving to an aluminum, which had a very hard anodizing on the surface of it, but they found that the anodizing still didn't hold up, and that's what's shown here. So there's a simulated bag shaper test that introduces this kind of an image. So what we did was, instead of the hard anodizing, we applied our nanobate metal to that same face, and after that same aggressive test, we were able to show that it holds up quite well. So this has been an interesting adoption for sporting goods. And yeah, just to summarize, we're really talking about very thin coatings here, so the addition of weight is still very minimal. And if we keep the thickness low, we're able to also process a number of parts very rapidly. Here's an example of some of those other parts that have made use of it. Okay, so the second family, the corrosion wear protection. Should be wrapping soon. So the cobalt family, the nanobate cobalt family that we manufacture, it's probably our most technologically advanced family that we have. One of the very first DoD projects that we had was in order to find an electroplated coating that you could apply to steel hydraulic bar and reduce the amount of hard chrome that's needed to be plated on these bars. Hard chrome is something that's sort of been targeted for phase out because the process itself is not all that environmentally friendly. There's a lot of negative byproducts that come with the process, and it's very expensive for treatment and cleanup. So finding an environmentally benign version of it that could have the same properties is very high on the list, still is to this day. This is maybe 8 years later after the original work that we did. So we developed this nanobate COP electroplating process, and essentially it's a drop-in for hard chrome. Except that when you compare the two processes, Nanobate COP and hard chrome, the Nanobate COP process is much more efficient. It allows you to process a larger number of parts with the same tank than you would for your hard chrome tank. So essentially take 4 tanks of hard chrome you might need, you can condense that down to 1 because the plating rate is just that much faster. It makes better use of the electricity provided. Better corrosion and sliding wear than hard chrome. And as I mentioned, this is probably our most mature technology. So right now, there are tanks in the US that have gone through a number of, a couple million amp hours, which is considerable for their application. But it's now got a mill spec, and an AMS spec is coming also very shortly for those kind of applications. And this is the one that's actually been licensed most. A couple facilities down in the US and as well as Canada have it. I think we're setting up one in Europe as well. I can maybe put you in touch with people if you're interested in that. Right, in terms of corrosion protection, so when comparing us to hard chrome, salt, fog, corrosion resistance is always of importance. So what we're able to show is that there's very significant difference between what hard chrome is and what our material is. Hard chrome, by nature, is microcracked. So this is a cross-section of your typical hard chrome plating. In a lot of ways, it makes it actually perform better. But in terms of sliding wear and the kinds of salt spray that we're requiring here, you can get Integran corrosion and some material coming off. Ours, our Nanobate COP, on the other hand, is pit poor and crack free, so it makes a very smooth and hard surface to be maintained. Yeah, just a couple results from our E117 test. We do a lot of this, and if there's something specific you want to see regarding test data, I'm happy to put you in touch with the right people. Okay, so this is that last family, the Nanobate high-load bushings. So this is what I think differentiates us, or provides a nice visual example of how we're different than conventional plating. You'll see the scale there. These are quite big, the largest one being about 2.5 inches in diameter, and the wall thickness is at least 1/8 of an inch thick, and that's without the flange considered. So with conventional nickel plating, etc., you would not be able to build out this amount of thickness and still have it as something that you can hold and you can put into a bushing and have it resist loads. And the same kind of thing goes for micro cracked hard chrome. You couldn't physically make a bushing that can stand up to these kinds of things. So this was actually developed as part of a second project for the replacement of copper beryllium. Copper beryllium is another one of those materials that's on our list for, let's try to get that out of our vehicles, engines, etc. The beryllium being a toxic component to that. So this is something that we came up with very recently. The program just ended maybe a year ago. So we're actively looking for people to generate these bushings so that they can validate for themselves just how well it works. The biggest benefit when comparing this to other materials used for high load bushings is when you have those very big bushings and you just don't want to deal with having to hollow them out to make an IDOD that's quite large, on the order of say 4 inches larger. Yeah, so I think that's pretty much what I have. This is just a little bit of friction coefficient data. Went along with that previous project to show our comparison to copper beryllium. And yeah, this is Rich Emmert. He's our VP of Business Development. He takes a lot of the incoming calls, but I'm also happy to talk to you today or afterwards. We've got business cards I can give to you if you'd like, and we can talk about it more. So thank you very much for the opportunity.